Welcome to section 3.3 where, wait for it, we're going to learn some shortcuts for derivatives. So derivatives are slopes of slope machines that tell you the slopes of all the tangent lines on a given function. So we're going to find a few shortcuts so we don't have to do that whole limit as h goes to 0 or limit as x goes to a. Now you might find that stuff fun, and that's cool. You will have to know that for the AP exam. We can now move on to some shortcuts so we can actually talk more about what we're doing and not how. I want to remind you of some of the notation here. This is pronounced df dx. That means take the derivative of f. Okay, or this is pronounced the derivative, d dx, of a constant is always 0. A derivative of a constant is always 0. And we know this because, after all, the function f of x equals 4, for example. This is just a constant flat line through 4. What would the slope of the tangent line be on that thing? Well, anywhere you draw a dot, the answer would be 0. So the slope is always 0. So therefore, the derivative of a constant function is always 0. So in this example, if f of x equals 5, f prime of x would be the function 0. That's a function. It always spits out 0, the derivative does. All right, let's move on. Rule number 2. This is the big one. We're going to be using this a lot this year. The derivative of a power function, like x to the 5th. What you do, listen carefully, throw the exponent out front, see how the n is going to go out front, and then you reduce the exponent by 1, and boom, you've got the derivative. So let's look at this example here. Remember, instead of doing the whole limit as h goes to 0 thing on this, we can use this shortcut. All right, so stay with me here. We're going to take the 8, and we're going to throw it out front. So the derivative is going to have an 8 as a coefficient. The base stays the same, and you're going to, now the formula says, reduce the exponent by 1. So you put a 7 there. Boom, you've just found the derivative machine, the derivative of this, and that spits out all the slopes of all the tangent lines on x to the 8th power. How cool and easy is that? We're now going to plug -1 in because they want to know, hey, what's the slope of the tangent line at x equals -1? Well, you just do 8 times -1 to the 7th. That would be -8. The slope of the tangent line at x equals -1 is -8. Or we say the derivative at -1 is -8. Constant multiple rule simply means if you have a coefficient to begin with, it just gets multiplied times the derivative of the other part. So you could think of this as 5 times x to the 6th. And we just talked about how to do the derivative of x to the 6th. So you throw the 6 out front. Okay, so this would be the 6 gets thrown out front, the base stays the same, you reduce the exponent by 1. However, the 5 is still there. The c, hopefully you see the c is still there in the derivative. So we take 5 times 6, and eventually you just do all this in your head. 30x to the 5th. 30x to the 5th. So to take the derivative of this, I would just say, hey, you're going to throw the 6 out front. 6 times 5 is 30. The base stays the same. Reduce the exponent by 1. Very easy. All right, there is a thing called the sum and difference rule, and basically it's kind of like limits. You can take the limit of each of these separately and then add your answers together. The same thing goes with derivatives. You just find the derivative of this, and the derivative of this, and the derivative of this, and combine them all. So for example, let's do this guy here. We're going to throw the 8 out front. We're going to throw the 8 out front here and combine it with the 3. So 8 times 3 is 24. The base stays the same. The exponent gets reduced by 1. Take a deep breath, and then you move on to the second term. Throw the 5 out front, multiply by -2. That's -10. x to the reduced 5 by 1 is 4. Take a deep breath and move on to the last term here. We're going to get plus 6x to the first. That's called the derivative. We did 3 little mini derivatives, and we just strung them together. Here we have a polynomial. Here's its derivative. We then plug 1 in. That's what this says. Find the slope of the tangent line at x equals 1. Often on the AP exam they have you plugging in 1 or negative 1 because it's really easy to plug into nasty polynomials like this. Equals 24 minus 10 is 14. 14 plus 6 is 20. So f prime of 1 is 20. That's the slope of the tangent line at x equals 1. And by the way, before I move on, can you imagine how difficult this would have been with the a plus h formula using a limit? It would have been horrible to do this because you would have to plug in x plus h on all of these spots. You have x plus h to the 8th power. That would be a Pascal's triangle mess. All right, let's move on. All right, find the equation of the tangent line on this function at x equals 6. This is a very standard problem. This will be on all the quizzes and tests as well as the AP exam. Let's set up a goal here, or I guess a strategy. First, we need to find a slope. And of course, we're going to use the derivative. And then we're going to use point slope form that we learned in Algebra 1. All right, so we find the derivative. And by the way, you can do dy dx, or you could write y prime. It's all the same thing. Okay, the derivative is. So why don't you think about that in your head just for a nanosecond. Come up with the derivative here. Maybe pause the video and then move on. All right, hopefully you got 4x to the third minus 2, and you're done. Okay, that's the derivative. You might say, well, what happened to the x? Well, there's an invisible 1 up here. You throw the 1 out front, reduce it by 1, you get 0. X to the 0 is 1, so this whole thing goes away, and you're left with just negative 2. And then remember we said the derivative of a constant is 0. That's why there's no plus 1 or anything here. So if you made a mistake, it's okay. Just learn from it. All right, we are now going to plug in x equals 6 to find the slope. So y prime equals 4 times 6 to the third power. Not sure why I'm using such a big number in my example, but it is what it is. All right, so we plug that into our calculator and we get 862. Boy, that's a very steep tangent. Very steep tangent, but that's okay. It is what it is. All right, now we do need a point. We do need a point, and we have half of the point. So please listen here, because this is another common question I get, is how do you get the y component? And I made a big deal about this last year also. Whenever you need the y component, you just run the x component through the original function. All right, so I'm going to put that through the calculator. I'm going to take 6 to the fourth minus 2 times 6 plus 1, and I get 1285, 1,285. All right, we're ready to go. We do y minus 1285 equals 862 times the quantity x minus 6. That's the answer. Maybe if it was a multiple choice question, you might have to convert it to y equals mx plus b form, but since I didn't say anything, just leave your answer like that and you're good. All right, make sure you're paying close attention here and you're not trying to do a whole bunch of other things and listen to this video, because the product rule is something that I'm going to catch you on all year long. So just learn to recognize when to use it and then how to use it. So that's your two goals right now, is understand how to know when to use the product rule and what on earth it is. Okay, if you have the product of two functions, let's call them f and g, then there is a formula for finding that derivative. And let me show you an example we're going to do on the next page. It's x squared times sine x. X squared times sine x would be an example of the product of two functions. All right, x squared times sine x is that your f would be x squared and your g in my notation down here would be sine x. Or, look right here, u would be x squared, and v as in Victor would be sine x, because we have the product of two separate functions. All right, let me show you how this works. So this says the product rule, the derivative of uv is u times the derivative of v plus the original v times the derivative of u. Now that doesn't exactly roll off the tongue, so it's more fun to sort of put on your Swedish accent and say u dv plus v du, u dv plus v du. So the derivative of uv is u dv plus v du, and you always start with u, right? You guys are sort of self-centered, right? No, just kidding. But anyway, you start with u. So right out the door, you start with u dv plus v du. Or you could come down here and say the derivative of f times g is fg prime plus gf prime. All right, this is something you might want to make a flashcard for and memorize, because you're going to be using this all year long. All right, let's move on to the next slide and actually put this into action. We are going to find the derivative of x squared sine x, and I do give you a little information. I say, hey, by the way, the derivative of sine is cosine. We're going to learn that later in this chapter, but for right now, just take it as a given that the derivative of sine is the cosine function. So we're going to find f prime. We're going to find f prime. Now, let's identify our u and our v. Our u here is going to be x squared, and our v is going to be sine x. All right, we're taking x squared times the separate function sine x. All right, so let's find u prime then. U prime is, remember, you throw the exponent out front, base stays the same, the exponent goes down by 1, it becomes a 1. 2 minus 1 is 1. And then I told you up above that v prime is cosine x. That's just a fact. Just trust me for now. All right, so let's find the derivative. Remember, the derivative d dx of u times v is u dv plus v du. Okay? u dv plus v du. So we're going to put u here, we got to put v prime here, plus we're going to put v here, and then u prime here. And this just takes a little practice. It's not difficult, just takes practice and getting to know this formula. So u is x. I'm just going to come over here to these four things, and I'm going to put them in. Here we go. X squared. Now we got to put v prime. V prime is down here. It's cosine x. So I'm going to put that in. Here we go. Cosine x. And then v is sine x times u prime, which is 2x. So I think I'm going to rewrite the whole thing now just to make it look a little prettier, because we don't like those trig functions to be out front. I'd probably write it as plus 2x sine x. That's f prime of x. And there she is. That's the derivative of that. It's not a composite function. It's a product function. We've got x squared times sine x. So you need to, remember I said you have to understand two things. When to use it, it's when you've got a product of two separate functions and you know their derivatives separately. We knew how to do this derivative. We were given this derivative down here. All right. And then how to do it is u dv plus v du. And if I had some Swedish music, I'd play it right now for you. But all right. All right, here we have another example. This requires the product rule because we have a function called u, we can call it u, and we've got a function called v. So let's write them all down. We got to write u prime and v prime down. I'm not going to rewrite u and v, but u prime is where you take the derivative of this guy, and you get 2x because you throw that 2 out front, and then reduce the exponent by 1. The derivative of 5 is 0. All right, now, why don't you take a moment and think about what would the derivative of v be? Hopefully you wrote 2x plus 5, 2x plus 5, because remember, the derivative of 5x, you throw the exponent out front, 1 times 5 is 5, 5, and then x to the 0 power is 1, so it just kind of goes invisible on us. And then the derivative of 8 is 0. All right, here we go. We got u dv plus v du is the Swedish formula for the product rule. So let's plug and chug, baby. We plug in u, x squared plus 5, and we plug in dv. dv is right here. That's going to be, we got to do parentheses. Why do we have to do parentheses? Because these are binomials and we're multiplying them, so you have to wrap them up in parentheses so they stay intact. Plus v. v is this trinomial, this big scary trinomial, plus or times 2x. All right, and there's our answer. I'm not going to bother multiplying all that out. You can, maybe, if it's a multiple choice question and they require you to do that, just make sure you foil here. This would need foiling, and then this would be 3 missiles here is all to multiply that out. All right, moving on. All right, the quotient rule. The quotient rule is very amusing here. We're going to deal with ho-hos, and if I remember, I'll try to bring some in for you. Some ho-hos for the quotient rule. So when you have the division of u and v, like, you know, sine x over x squared, we got a whole different rule to use. We have a whole different rule to use, and I know it looks kind of crazy here, but we'll make it pretty easy to remember. The derivative of high over ho, and how can we remember that? Well, high is up high, right? And ho is down low, I guess you could say. All right, and yes, there's some funny stuff there, but I'm just going to leave that out of the video, if that's okay. Okay, we're going to have a formula, and here's how it goes. Ho d high minus high d ho over ho ho. Ho d high minus high d ho over ho ho. Okay, so the ho is first. The ho is first. And again, I'm just not going to comment on that. We'll talk about it in class. But the ho is first. Ho d high over high d ho over. And then just picture a ho ho on the bottom there. That's ho squared. Ho squared. So when we say ho ho, what we mean is the v squared. So the actual formula would be ho. That's your bottom. That's your bottom here. Ho is on the bottom. So ho, so here would be v du minus u dv. See, it's kind of similar to that product rule, but there's a minus sign, but you combine them all just with the derivative of the other. So v du and u dv, but they get subtracted in the quotient rule all over the denominator squared. The denominator squared. So if you want to say it in Swedish, it would be v du minus u dv all over v squared. All right, but it's more fun to say ho d high minus high d ho over ho ho. And just remember, the top of the fraction is up high. So that's what my brain does when I try to sort out where high is and where low is. Sometimes it's, if you go on the internet, out there on the interwebs, and you look at this formula, they might have the word low over here. High over low. So it would be low d high minus high d low over low low. But that's not nearly as much fun as saying ho d high minus high d ho over ho ho. Okay, and we don't get to eat ho-hos then either. All right, moving on. All right, we have an example. We have an example of a quotient, and we need to divide. We need to use the quotient rule. The quotient rule is given high over ho. We always start with the ho. So it's ho d high minus high d ho all over ho ho. All right, so ho. That's just the bottom unchanged. That's just the bottom unchanged. It's just the lower function there. And now we write the derivative of the upper function here, the numerator function. The derivative of that guy is going to be 3x squared minus 2. And then we slap a minus sign and put 2 more parentheses because we have to put high all untouched. High untouched. we have x to the third minus 2x plus 1, and then right at the end here we put the derivative of the bottom, 6x, all over the denominator squared, and the denominator is 3x to the fourth, or 3x squared, sorry. X squared squared. So that's why I was thinking to the fourth. So we're squaring the denominator function. Okay. So what is the rate of change on this crazy rational function at x equals 1? Well, all you have to do is plug 1 in anywhere you see an x. So the answer would be 3 times 3 minus 2 minus 1 minus 2 plus 1 times 6 all over 3 squared. So that's going to be, I'm kind of running out of room here, so I guess I can move this up like that. This is going to be 3 minus, all of those cancel. 1 plus 1 is 2, minus 2 is 0. 0 times 6 is 0. So all over 9. So 1/3. That's the rate of change, up 1 over 3. That's the slope of the tangent line at x equals 1 on that crazy rational function. And we really did all that pretty fast using the very cool ho-de-hi minus hi-de-ho over ho-ho quotient rule. All right, so you got to practice it on homework, and you got to really make sure you're doing it right. And ask me questions. Check the solution manual to make sure you're doing it right, because that's going to be used all year long. All right, negative exponents. Hey, it's the same rule as earlier. Throw the exponent out front and add -1 to the number. Same thing, right? N minus 1. But I want you to think about it as adding -1, adding -1. So, for example, given the following function, 3x to the -5th, what would f prime of x be? Well, remember, we take -5 and throw it out front and multiply by 3. So that gives -15. The base stays the same. Now, I need you to think a little differently. We're not going to minus 1 per se and get 4. We're going to add -1. So that we don't screw this up, we're going to get -6. -6. So -15 x to the -6th. Now, I want you to remember that negative exponents actually mean 1 over. So this answer will probably be, on a multiple choice, you would see this as your derivative. That's your derivative function. And the original problem was 3 over x to the 5th. 3 over x to the 5th. There is a thing called higher order derivatives. It sounds scary, right? Higher order derivatives. Well, all that means is you can find the derivative, which is called f prime, but you can also find the next derivative, which is called f double prime. So let me give you an example here. Given f prime, or f of x, is 3x to the 4th minus 2x to the 2nd plus 1, let's find the derivative. Well, that's pretty easy. We just throw the exponent out front. That'll be 12x to the 3rd minus, the next one is going to be 2 times 2 is 4. Reduce the exponent by 1, you get 1. And then the derivative of a constant is 0. All right, now you could take, this is called the second derivative, and we often write it like this. F double prime of x is, and you just do it again. It would be 36 x squared minus, now 4 times 1 is 4, and x to the 0 power is just 1, so we don't write anything there. And then if you're really excited, you can just keep going, or maybe they ask you to find the third derivative, and you simply find f triple prime, and it's going to be 72x to the 1st plus 0. And then the fourth derivative, 1, 2, 3, 4 of x would be 72. So you're just finding different derivatives. We're going to be using this a lot in the next chapter because, and chapter 5, because the second and third derivative actually tell you some more exciting stuff about the original function. All right, so we're going to use all of this to tell us information about the original function. All right, good luck on your homework. Make sure you go back and review that product rule and the quotient rule, and we'll talk about that more in class. All right, thanks.